Let me start recording. All right, thankfully, we just had one slide left for the ferroelectric memory, which we'll quickly finish up today, and then we'll move on to a new lecture, right? Phase change memory today. So we discussed the pros and cons of ferroelectric memory. We covered mostly all of it, except for one, and that is a unique problem that ferroelectric memories experience, okay? That is the problem with fatigue and wait time. What is that? Folks, in a ferroelectric memory, if you remember the PV loop, oh, I'm sorry, I forgot to select HDMI. Give me a second. All right. Okay, so thank you. What I was gonna say is that in a ferroelectric memory, if you look at the PV loop, quick quiz, meaning which parameter of the ferroelectric will be related to the distinguishability of the stored data? Which property would you like to increase? Is it this switching points plus VC minus VC, also known as the coercive voltage? Or is it this remnant polarization, plus PR, negative PR? Which one would you like to enhance? Polarization? You guys all okay with that? Sure. Because we use positive and negative polarization to represent 0 and 1. So the farther the difference is, the better it should be in terms of memory stability, right? And reliable sensing. So having that idea in mind, when you see a situation that we are plotting remnant polarization, and basically this plot is normalized with respect to regular polarization, but just don't worry about it. Consider that this is remnant polarization. And these are real data, as you can see, right? From published papers. What would you say when I show you that the remnant polarization, this is positive, this is negative, the difference between them is increasing? I haven't even told you the problem or the feature that I'm going with. But just looking at the data, would you like this part of the trend or not? This is positive polarization, positive remnant polarization. This is negative remnant polarization. And the separation between them is increasing. Is it good or not? What do you think? Yes, we just discussed this, right? The larger the difference is, the better it is. Okay, sure. I mean, as long as it is improving, I'm good. Because maybe you can find a way to have a sense reference in between. And then all you're doing, you're just getting better. Basically, your sensing is becoming more robust over time. But then notice the other side here. Do you like this portion of the curve, folks? Why not? Because now it's going in the other direction. It's basically reducing my remnant polarization differences. So that's what, notice the top level of the figure. This portion is called fatigue. So apparently, when you use a ferroelectric material over and over again, initially it takes some time to fully wake up. It has to do with the domain dynamics internal to the ferroelectric material. Okay, to make sure all the domains are responsive, you have to go through for a few cycles. That's known as the wake up phase of the ferroelectric. Okay, after you wake it fully up, it's like human being, as you see, like we take some time to fully wake up from sleep, and then we get tired towards the end of the day, almost like that. Okay, so think of it that way. The ferroelectric takes some time to fully get to the potential that it could provide. But then soon after, it starts showing some tiredness. And apparently, it loses the distinguishability over multiple cycles, which you do not like. So as a circuit designer, when we plan, we should plan for the best case scenario or the worst case scenario? The worst case scenario. We should definitely plan for the scenario that we get after fatigue takes place. All right? So this is a known challenge for ferroelectric, but we have to account for it in circuit design. And the figure on your left shows an example of that. Notice this is current versus electric field characteristics, and the blue dotted lines is the pristine ferroelectric. So in a pristine ferroelectric material, you don't really get much capacitive current because it doesn't even really work as a good ferroelectric at the point. But as you keep cycling it and go through the wake up phase, that's what the black line shows you, you get the full potential, you get the highest difference in current spikes for two polarization levels, right? Positive and negative. And then finally, after you go through multiple cycles, you get the red dash line, which is slightly degraded, but it works. It's not the end of the world, but you cannot really shoot for the peak performance from ferroelectric memory because they will quickly be fatigued. Are you all good so far with it? Yes. Great question. So, like I said, they're not being sold yet. Okay, there was a time when we had ferroelectric capacitor, but ferroelectric FET memory, they're still in the R&D phase. Okay, some industry players like Fraunhofer IPMS in Germany and some others here and there, they're trying to bring it to market, including Intel, by the way. Intel has some interest in ferroelectric memory, but some of the things that are setting them, aside from the competition is issues like this. How do you benchmark your designs against others? If you benchmark after fatigue, then it's confusing. If you benchmark before fatigue, then it could be misleading as well. So as of now, in terms of commercialization, we are nowhere with ferroelectric FET. Okay, but if we do, we definitely have to, without any doubt, have to report what you get after fatigue, because look at the number of cycle. 10⁶ is nothing. Okay. Rule of thumb, typically a memory is considered good if you could at least go over 1 billion cycle, 10⁹. That's the rule of thumb. If you cannot cycle something beyond 10⁹, at least, we typically don't consider that to be competitive, because there are other solutions like spintronic memories that could go to 10⁻², for example, right? Then why would we settle for something less? Okay, now, yes. Yeah, that's a good question. It will probably not decrease as, like seriously. It will probably saturate, but for some memories, and I'm going to show you in the next slide, depends on what type of ferroelectric material you're using. Okay, so typically people are trying to dope the conventional ferroelectric material with different elements, including zirconium and silicon. These are the two things that I personally worked with. Apparently they make the ferroelectrics better, and they also help with the fatigue situation. Okay, so it's possible to make it saturate and not degrade any further, but if you just deal with any raw ferroelectric, there are certain materials which will basically diminish. Okay, all right. So notice, in terms of endurance number, they are not too bad if you use the right dopants. So you cannot just negate them based on these numbers. Hey, 10⁻³ is nothing, but don't shoot for 10⁻³, shoot for 10⁻11 and beyond. That's the endurance number we like. And this is just taken from a different source, but it gives you the same picture. Okay, wake up and then fatigue. And the answer to your question also lies here. Notice the red line shows continuous fatigue. The blue one, on the other hand, is kind of saturating. Okay, and also beyond a certain number of cycles, like 10⁻⁹ or 10⁻⁻10, you will not get those data, mostly because people don't have enough time to test them. Okay, remember, if a device is switching in a nanosecond, that means having 10⁻⁹ cycle is about a second. See that? But typically, when we test devices in a lab environment, we have much bigger samples, and they take maybe like a microsecond to switch. Then it becomes challenging to try too many cycles after a certain threshold. That's why we don't always have the numbers for those devices. Did I answer your question? Okay, so that brings us to the close of this particular technology, ferroelectric memory. And notice the comparison table, which I don't want to go over right now, because we'll start with this same table in the next lecture. So let's start the next lecture and then discuss this table. Okay, this is supposed to guide you through the overall landscape that we have covered so far. Okay, so before we begin, the next topic would be about phase change memory, or PCRAM. Before we begin, I want to show you where we are right now, how much we have covered, and how will this memory compare against all the others we covered. So did we talk about SRAMs, DRAM, STT-MRAM, ferroelectric memory that we just concluded, FEFET and FERAM, right? What is FERAM? When you use just a standalone ferroelectric capacitor. What is FEFET? When you use ferroelectric capacitor at the gate step. Are we all good so far? So we covered all of them. Now we are at PCRAM. So we are actually heading towards almost closing up this table, except for one. Notice we conveniently skipped flash memory. And here is why. Your Wednesday's industry lecture will be on SSDs and flash memory, Wednesday. So on Monday, I'll give you a brief overview we'll begin with the basics of flash memory. Okay, that way you will have those basic concepts fresh in your mind so that you can benefit the most from the industry lecture. Does that make sense? If I covered it like way ahead of time, then you probably would have forgotten. I didn't want that to happen. So that's my plan, to cover it on Monday after we go through the PCRAM lecture today. Okay, so notice, let's take a look at each one of these rows. And we have never done this with any other memory before, but now we have covered enough to take a step back and compare them against each other. Just in terms of cell size, which one is the worst, folks, so far? Are you surprised? Why not? Which memory uses the most number of transistors? SRAMs. So no surprise there, right? Obviously. But in terms of speed, notice the write speed, for example. Who's the clear winner? Just take a look at the row corresponding to speed, SRAM, right? Did we discuss this before? So you haven't seen that in a tabular format before, but we did discuss this type of pros and cons and advantages and disadvantages in comparison with SRAM and DRAM for all the memories that we covered. Okay, so this is just a more structured tabular format. So I will not go through all the rows even now. We will revisit this, journey through the memory lane after we get done with the rest. That way we have a more comprehensive discussion, right? Just wanted to show you, here we are almost, heading towards the technologies that we'll end with. And then obviously there will be logic in memory and cryogenic memories in the course. Okay, so today's technology uses a completely different phenomena to store information. As we all know, we need two physically stable states to represent logic 0 and 1. For ferroelectric, it was two polarization states. For MTJs, it was two magnetization states. For DRAM, it was two charged state of the capacitor, either charged or discharged, right? So for this particular type of material, we'll be dealing with two crystal structures. Have you guys heard about amorphous and crystalline structures? Especially 335, we definitely covered it, right? Polycrystalline, amorphous. But if not, the name tells you what it is. Think of sodium chloride. If you see the crystal structure of sodium chloride, it's nice and uniform everywhere, right? It's a crystal. But there are materials where you don't see such a really nice uniform crystal structure. They're often called amorphous. Okay, they're polycrystalline as well, somewhere in the middle, but we are not getting there. So turns out there is a family of material that can be electrically programmed to be in an amorphous state where you don't have any long range structure. Or you could use the same material and do something to it and convert it to be a fully crystalline structure. Turns out, why would we do that, right? Turns out in a crystalline structure, this material provides low resistance and amorphous high resistance. You see where we're going with it? So basically, we'll be using this low resistance state to represent logic 1 and high resistance state to represent logic 0. That's the goal. Okay. And there are two things that we have to maintain. First, we have to be able to sense it electrically. We cannot just go and see, is it crystalline? Is it amorphous? We cannot visibly do that. We have to do it electrically. And it shouldn't be difficult to do because they give you two resistance levels. You know that already, right? We have gone through this a couple of times already. When you apply a constant voltage to both of them, they will generate different levels of currents. That's how you sense. Super simple, similar to STT-MRAMs as well. And then you have to find a way to program them electrically. But I haven't told you how to flip from or switch from crystalline to amorphous. I just told you there is a way. So let's see the way. All right. That comes up in the next slide. All right. Take a look at this structure. This is where this fancy phase changing material lies. This is GST, germanium antimony telluride. But don't take it as a one-off. I'll show you other materials in a slide that is coming up soon. But just take this material to be the golden material as of now. Okay? And it actually is the golden material in industry. So GST. And on top of it, you have an electrode, metal electrode. At the bottom, you have an electrode, and you have some thermal insulation around it. Why is that? Because we're trying to channel current through the material. What that current does is it generates heat because, I square R is the resistive heat that we generate when we flow current through a resistor, right? And we design it this way so that you could put provide the most amount of heat, channel the most amount of heat to this material, GST. And what we're trying to do is, surprise, melt the material. Well, would you ever like something to be like, so you have a circuit and you're trying to melt something on the circuit. Is that a good thing? Typically not. We typically don't associate melting things on a chip with something good. I wouldn't blame you, because let me just take a step up to the next slide and I will get back to the previous slide. I always love history. I want to show you where this thing started. Let's zoom in. 1962 is when somebody proposed and showed a phase-changing type material, and that was a different material platform, as you see, based on arsenic, but it is a phase-changing material. But then people didn't really take it seriously for electronics for a while because of the same reason. Hey, man, you are literally melting things on a chip. I mean, we cannot use this. Okay, this is too crappy in terms of energy efficiency, because it takes a lot of energy to melt something, as you can imagine. And that used to be the case. But notice, all of a sudden, there was a big gap in between, and then all of a sudden, we started having more activities. And I think the other figure right here, take a look at this diagram, will make more sense. This is the number of patents. This is not technical, but I think it gives you some technical sense. The number of patents awarded on PCM technology, starting from 1966 up to 2008 or so. Apparently, there was nothing. And then all of a sudden, there is a spike that tells you something. Something happened around this time frame, which suddenly led to increased activities about phase change memory. And everybody seems to like it now. What changed? We still melt them, by the way. Nothing changed, okay? Still kind of cook them on the chip. But what changed is, let me tell you, nanotechnology. So at the time in 1960s, we used to have big chunks of materials. And turns out the energy it takes to melt something is related to the volume of this material. Okay? When you make things from micrometer scale to nanometer scale, how much volume are you reducing? Can you imagine that? Should I tell you the number? 1 billion times. Imagine, micrometer to nanometer is 1000x reduction. But that's in one dimension, length, width, and thickness. So in volume, you are basically reducing 10⁹. So you reduce the volume 1 billion times. So the energy will definitely, energy to melt something down will reduce dramatically. Okay, and that's what happened. And people suddenly realized, hold on, the same thing makes sense now. Why don't we revisit and use it as a memory? And that's exactly what happened. Does that make sense? So don't negate the ideas back in 1950s and 1960s and whatnot, simply because they don't, they can become technology relevant several decades down the line. And that's exactly what happened to PCM. Okay, since we, anyways, fast forwarded, let me backtrack and cover these slides basically, right? So we covered this slide. Let's cover the slide right before it. Notice in 1970, you used to have a technology node that was, you guys know what technology node is, right? This is the size, basically the gate size of the transistor. So we used to have bigger transistors. Now we have smaller transistors. Super simple. And basically, by going through the timeline, you see we are making the transistor technology smaller, and at the same time, the PCM themselves are becoming smaller. Why? Because when we find out the way to make small feature size for transistors, we also discover ways to make small PCMs. Does that make sense? This patterning etching technologies improve. And apparently, we could make smaller PCM. One other thing, it's a fun thing that I want to point out, always GST. Notice, we changed from decades to decades, but for some reason, it's still the magic material. And there is an interesting reason, I'll tell you that. So let's backtrack to this slide again. I just wanted to have it as a nice history lesson. This is taken from 1978, from an IEEE publication. So that shows you back in the even before 1980s, people tried and basically gave up on PCM simply because of not having technology relevant, fabrication capability. All right, now taking all the way back to the slide that we were in. Are you guys with me so far? Or are you lost? Okay, let's go back here. So did I tell you that you can convert this material to a high resistance state by making it amorphous, and then you can make it crystalline, as you see here, and make it low resistance state. That's what we are after. But now I'm going to tell you how. And this structure kind of gives you some hint. We melt the material, and when you melt, you give it an opportunity to change its crystal structure. Not every material will do so, by the way. Some of them will, and GST is one of them. Okay, but there is a certain approach that you have to follow to switch from amorphous to crystalline and crystalline to amorphous, and that comes up in the next slide right here. Okay, are you ready to pay attention to this? I know it's a busy slide, but hopefully if we pay attention, we'll get through this together. Okay, so this is, just look at this structure. There are 3 colors. Why? Because they represent GST, germanium, antimony, telluride. 3 different atoms. Do you think this diagram looks like a single crystal or amorphous? What do you think it looks like? Basically, it's all over the place. There is no structure. So it's amorphous. So you're going from amorphous to crystalline. What you have to do is you basically have to melt it down to organize it. Right? You first have to break it to make it, essentially. So just melt down the amorphous material, which is in high resistance state, and then let it settle down slowly. That's the key. Okay, take a look at these 2 pulses. We basically use current pulses to melt. So we'll be melting them anyways, for sure. But in one situation, we'll be giving the material more time than the other. So when you rush, atoms don't get enough time to organize and create a single crystal or crystal structure. But when you give it enough time, they organize, they minimize their energy, and they get to a really nice crystal structure. Okay, so when you try to go from amorphous to crystalline, you increase the temperature, and we basically don't have to melt it. We have to go above the crystalline temperature. So there is a temperature threshold underneath the melting point, and if you go up above that temperature and then let it settle at that temperature for a while, it will reorganize and become crystalline. So there you go. You have electrically programmed the material. Why electrically? Because you have used a current pulse. Okay. Number 2, this is often called fast quenching. So basically you use a really sharp current pulse, really high current. So it immediately creates a high temperature, and you go above the melting point. This is melting point. And then you quickly take back the current pulse. So you don't get the material enough time to settle down or organize itself. So then it becomes amorphous. Very simple concept. And that's why, I mean, it dates back to 1960s. What do you expect, right? So most of the advanced approaches like spintronic memory, for example, or ferroelectric memory, they were not even invented back then. So this was the concept of its time. Okay. Are you all with me so far? I know it's a busy slide, but we are covering together. Did we cover this 4 diagrams? What does these diagram tell you? Can anybody summarize? Yes, basically it tells you the pulse shape and what happens to the temperature. For one case, you need a longer pulse and you don't create that much high temperature. For one of the cases, you need really sharp pulse and you go above melting temperature. That's exactly what was covered here as well. All right. Yes. So this is the thing. This is temperature profile. The current profile may or may not look like that exactly. And we will talk about thank you for the question. That's a great question. I'll show you the current profile here. Okay, it's a little bit more complicated. We're getting there. But thanks for asking ahead. All right. Any other question related to what we covered so far? What I didn't cover is this current profile, IV, right? These are 2 cartoons. Why cover cartoons when you have real data coming up? So I'll first cover the real data, and then I'll show you what these cartoons are trying to tell you. Are you all good? Okay. So I will track back a little bit to the previous slide. And what this slide tells you, it shows you a flowchart kind of thing, a feedback loop, but it has a meaning. Can anybody see something unique here in this flowchart? Have you ever seen this kind of a flowchart for any other memories that we covered in here? No. Why? We didn't have to. For most other memories, we just had to deal with voltage and current. But in phase change memory, there is a complicated dynamics involved. First, structural dynamics. So depending on the crystal structure, its electrical property changes. And the crystal structure itself changes because of a thermal interaction. And the thermal interaction is dependent on the electrical system itself. Is it high resistance or is it low resistance? For example, as we talked about I square R, when you have higher resistance, for the same current, you generate more heat. But then when you generate more heat, you change the crystal structure, and that changes the resistance itself. So there is a complicated feedback loop within this material, right? So it's more complicated to model and explain than most other memory materials that we discussed so far. I just wanted to highlight that. So when you try to make models for this type of materials, you have to have 3 different independent modules that should be cross-coupled and that should talk to each other in a self-consistent way. You have a structural dynamics module, you have to have a thermal module, and then the IV. But it's not independent at all, like the other memories. All good? Okay. So again, I tend to get ahead of myself, so I'm tracking back. I think we could cover this slide now. We're ready to cover this slide. You might have a question. I've been showing you GST is the magic material. GST is the magic material. So that means we have a magic material from somewhere that somebody discovered, and then we are just living with it. What if we run out of the GST material, right? These questions are all legit, right? I just wanted to highlight that's not the only material. So take antimony, germanium, and tellurium, and you can come up with different alloys this way. It's like a material triangle, like a ternary diagram. Okay, you mix different percentages of these 3 materials and come up with different combinations of GST. So they're all GST, but their properties will be so diverse that you'll be surprised to see them. Okay, for example, if you have tellurium rich GST or antimony rich GST or germanium rich GST, you have very different properties in terms of resistance levels, in terms of switching threshold, in terms of crystal temperature and melting temperature. All of these will change. So that creates a really nice, ripe venue to optimize the material further and explore. But then people didn't want to stay within a GST only, right? They started testing with other material. Instead of germanium, you could try indium or tin or so on. And similar to others, instead of antimony, you could try bismuth, gold, or arsenic. So the point that I'm trying to make is GST is certainly not the only material. Within the GST system, there are unlimited material possibilities, and they're all different, vastly different from each other, okay? So this is good. We love tunability. Yes. Yeah. No, this is not the lattice plane. Basically, what it is telling you is, imagine you start with antimony and germanium. How much of each material are you mixing with each other? Okay. So for example, if you take 1 point, how much of antimony, how much of germanium, how much of tellurium are you mixing to get this GST? So this is an interesting way to represent the percentages. You could also just list them in a table, but it looks more fancy and easier to track if you plot them in a table. Yeah. I'm sorry, could you? Yeah. So that's an equal distribution for all of them. Yes. So that's one approach. Or you could make one of them to be the richer entity. Like, for example, if you go towards this direction, which is almost 100% tellurium, that's becoming tellurium rich, or antimony rich, or germanium rich. And people try to make them something rich for some specific agenda. If you're trying to go after high on-off ratio, do X. If you're trying to go after lower switching temperature, do Y, something like that. And all of these were experimentally tested for years. And Micron Technology, the company that you probably know about by now, they invested a lot of time and energy and money, of course, testing this material, quite thoroughly, I would say. All right. Okay. So now that you know it's not just one material, hopefully that gives you some satisfaction. But also, this is taken from a chemistry literature. I'm not an expert in that, but I really like this figure. It shows you that people tried with, there are physical and chemical reasoning behind why it does what it does. Why GST system does this kind of phase changing behavior, but not the others, okay? And this are related to the lower level chemistry, which I'm not definitely getting into, uh, apparently it has to deal with the hybridization and ionicity of the underlying atoms. So the chemists know how to figure out the appropriate material system to try out phase changing behavior. Okay, does that make sense? So for example, they tried a lot of different combinations, but only these green ones showed phase changing characteristics. And notice all of these ones are related to germanium antimony telluride mostly in their experiment. Okay, so all right, all of these slides have been covered. Let me take a step back here before I move forward and see if you have any questions. It's a great question. You already noticed. I didn't want to cover it here, but I will. Yes, we have negative differential resistance, which we'll be talking about in a few minutes. All right, let's move to the next slide. And please feel free to stop me if you are feeling lost. Have you seen this before in several other memories? So essentially, doesn't matter whether it's a PCM or an MTJ, this is giving you two different resistance levels. So in terms of array structure or the approach towards read and write, nothing changes, except for one, the programming. The programming is different for phase change memory versus STT-MRAM versus others. As you can see, we need different current pulses of different timing. So that's the unique feature of PCM versus the other memory. But in terms of the cell structure, you still need a PCM cell and a transistor. What is the transistor doing again? Basically access device, right? It's letting us access the ones that we want and not access and not disturb the ones that we don't want. All right. So anything new here in the array structure? Should I go over this again? It's exactly the same array structure as STT-MRAM. You have bit line, you have source line, and you have word line. Word lines are shared across row. Anything new that you see here that catches your eye? No? Should it be similar? What do you think? What do you think? What did we do for STT-MRAM, folks? We had to pump in some current to switch the MTJ. How should I switch the PCM? By pumping in some current. So exactly the same thing, except the fact that, yeah, now we need two different amplitudes of current versus two different directions of current in MTJ. MTJ required two different directions. PCM requires two different amplitude and timing, pulse width, right? So pulse shaping is necessary for PCM. All right. Now, moving to the most difficult slide of today's lecture. Okay. If you pay attention, hopefully we'll get through this together. Ready? Do I have your attention? Full. Okay. Let's do it. So when you see this type of characteristics in a current voltage property, I always like to use real data. And then, of course, something to explain. But this is also real data, by the way, from experiment. What can you comment about this in a current voltage scenario? I already got a comment, but can someone else add? What does that represent? Negative? Yes, negative differential resistance, NDR. Did we see that before? Yes, we also saw negative differential capacitance, right? Negative capacitance instead. But why are we getting that? First question. And why only in this side, not the other side? Okay, I'm gonna explain that to you. So before doing so, let's go through one of these curves and then follow along its journey. So I'll be marking on top of it. You have to see it live to understand. Okay, so I'm starting from this point. Can someone tell me, is between the blue line and the green line, which one has higher resistance? This is current voltage plot, by the way. Between the blue line and the green line, which one has higher resistance? Why are you so nervous? Blue line, right? You have really low current for the same voltage. That means this one must have higher resistance. That also tells you that represents the amorphous state, because in amorphous state, you have higher resistance, okay? So let's do that. So what happens when you just keep the material in amorphous state and you are not basically melting or changing anything? You are just applying a voltage and trying to figure out how much current you get. It's a resistor afterwards, right? So you apply more voltage, you get more current. Is it surprising at this point? Up to this point? No. Pretty natural. You get more voltage, you apply more voltage, you get more current. Okay. What happens to the green line? this is considering that you somehow program the material into crystalline phase, and then you are applying voltage, and the more voltage you apply, more current you get. So they are independent with each other. Can you draw them independently? Do they make sense independently? Okay. Now, apparently there is a switching point right here, and let's talk about that switching point now and see what happened there. So at this point, this is what we are doing to the PCM. You have a resistor in series with the PCM, and we apply the voltage across the stack. So you have two resistors connected, PCM and a load resistance. I mean, are we doing it deliberately? Get to the previous slide. When you have a PCM, you have a transistor connected to it. What will the transistor bring? A resistance. So basically, we are mimicking the structure that we get in a memory cell. We get a PCM and a resistor in series. And that's what we're doing in this experiment. Are we all good so far? Okay. So at this point, the PCM gets enough energy. You have enough current that could generate enough heat to start melting or changing the crystal structure. So at this point, the crystal change starts. I guess still with me. Notice this region have been marked as amorphous but on, and the other region here, it's amorphous off. So basically it is amorphous and it is staying amorphous, but beyond this threshold it is still amorphous. It hasn't crystallized yet, but it is trying to turn on gradually. It's trying to reorganize. So that's amorphous on state, and the other region is amorphous off state. Are you all good on this? Any confusion so far? Okay, I haven't explained why it is going back though. I will now. Okay, tell me, if I apply 10 volt across this stack, I have two resistors. One of them is 1 kilo ohm, the other one is 9 kilo ohm. Which of these two resistors will take the greater share of the voltage? 9 kilo ohm? Okay. You guys seem really tired today for some reason. You can speak up. It's okay. You can be wrong. 9, right? You're right, actually. But basically, you can be more confident. That's what I'm saying. Sure, the greater of the resistors will take greater share. But then what happens to a PCM when it starts changing? Its resistance decreases. And there is a really sharp difference between the crystalline resistance and amorphous resistance. Okay. So all on a sudden, it dramatically changes its resistance. So then what? It was taking the greater share of the voltage that you applied. When it switched, it basically gave back the voltage to the other resistor. All on a sudden, the other resistor is the dominant one now. So when it switches, it becomes smaller than the load resistance, much smaller than the load resistance. So there is a voltage redistribution. Does that make sense, folks? So the voltage that you are plotting here, that is the voltage across the PCM. What will you see when you experimentally measure this? Yes, the PCM was taking most of the voltage at some point, but when you cross this point, it immediately gives up its share to the other one. So what happens to the voltage across the PCM? Will it increase or decrease? It will decrease. So that's why you see a snapback. For the same current, for example, at this point, as the current increases further, instead of increasing the voltage, it basically decreases the voltage because the resistance is decreasing. V equals IR. Even if you keep increasing current, if your resistance keep decreasing, what happens to the voltage? Decreases because the resistance decreases dramatically. Okay, and that's why the voltage across this PCM decreases with increasing current, and that's the signature of what? Negative differential resistance. Does it make sense? It's a really nice phenomena that we observe in PCM. And once it gets to the point, when will we say that it's a memory switch? Notice this is necessary. This is more complicated than other memories that you have seen. Okay, even when you are here, if you let it go, it hasn't switched the memory. It will basically still be amorphous. You have to wait and be patient. Did I tell you that your pulse will have to wait for a while to let it completely crystallize? So this is the point where it crystallized and switched over entirely to the crystalline state. And once you are there, you could just stay like this. Does that make sense, folks? I guess all good. Yes. Great question. Yes, absolutely. Remember, there are two things. Yeah, go ahead. Sorry. Absolutely, you can, for sure. So apparently there is a resistance balance between these two entities, right? The two things. Can it be theoretically done? Yes, theoretically it can be done. Can it be practically done, or can we use it in real life situation? No. The reason is the transistors are designed in a way that when they're active, they give you the lowest possible resistance that they can provide. Okay, you have to make sure they don't disrupt the overall read current. Otherwise, they will sully the distinguishability, as we discussed in the STTMM lecture, right? So they're designed to be as if they're not even there when they're on. So that means their resistance is so insignificant compared to the PCM that modulating transistors will not really make much of a difference. But if we choose to make them more dominant, it's theoretically possible, but practically not done. Does that make sense? Okay. All right. So I hope we understood this cycle, that you cross over from amorphous to crystalline, and then once you're in crystalline state, if I remove the voltage, imagine for a second I remove the voltage after making it crystalline, and then I restart. What happens then? Which curve will it follow? Will it follow the blue one or the green one? Green one. Why? Because it is non-volatile. It remembers that, hey, I was crystalline before. So that means next time you basically just observe this current level. Yes, there was a question. Yes, that's a great question. So basically, that's the point where you have hit this crystallization temperature, this temperature, crystallization temperature. And then you have to wait up to this point to make sure all of these atoms could reorganize and crystallize. Okay, that's why there is a time involved. And this is a very confusing curve for two reasons. First of all, notice this is supposed to be a DC curve because you have current versus voltage, no time involved here. But all of these are linked with time. If you don't give it enough time, this point will not even make sense, right? So this is known as pseudo DC property. There are some signatures of transient properties here, but we are presenting it like a DC characteristics. So that's why it's more complicated and confusing to most people when it comes to the other memories that we discussed. Okay. Are we all good? Yes. Great question. Yes, I'm going to tell you. All right. So basically, you follow the same approach, but now this is more aggressive, I should say. I don't know if that's the right word, but abrupt maybe, or disruptive. So what you do is you apply a really sharp current spike. What you're going after is basically melting the material. That's where the melting comes. The first approach when we are going from amorphous to crystalline was not about melting. It's about just initiating the lattice redistribution. Exactly. But now it's all about melting and disrupting stuff. You have literally melted the material, but now you don't want to give it enough time to reorganize in a nice way. And that's what you get out of the material. You get amorphous. Okay. So basically, we typically don't plot the other one in current voltage characteristics because you get really nice snapback region from high to low. But when it comes to low to high, there is a reason why you don't see that much of a pronounced S curve. You get some snapback, but not as much as this one. Okay. The reason is the resistance of this PCM is so low at crystalline state that it's lower than the resistor, the load resistor. Let me take some numbers, say 5 kilo ohm and 4 kilo ohm. So then they share almost equal parts of the voltage. And when there is a snapback, it's not as pronounced, as dramatic as what you see moving from high resistance to low resistance. And if I tell you some numbers, it will make more sense. High resistance state could be as high as a giga ohm. Low resistance could be as low as a kilo ohm, for example. So there is a huge difference, right? So switching from 1 giga to 1 kilo changes things dramatically, and we typically portray that in these IV properties, but the other one is typically not shown in DC format. And the reason I just explained, this is not really the right way to see it, because there is no time that you see in this IV properties. The right way to see it would be to do what? to see pulse, current pulse. Or not? Did I answer your question? Okay. Any other question? Yes. Yeah. That's a good question. So we don't typically maintain the voltage. We apply the current. We try to maintain the current level. Okay. So we use a constant current source to maintain the current. And the voltage is basically what you get from resistance. And like I said, V equals IR. If you maintain the current constant, when the resistance reduces, the voltage reduces with it. So that's what you see here. As the resistance reduces, even if you keep the current the same, the voltage appearing across it will reduce. Okay. Yes. So this is V applied basically. It so that's another good point. When these guys, this is taken from a source, as you see, right? Uh, this is taken from a journal article. When they did this experiment, instead of applying constant current and measuring voltage, they applied constant voltage and measured current. So basically, they did the experiment in a flipped way, but plotted with respect to current voltage again. Okay, that's where some confusion comes in. I understand, and thanks for asking that question. But typically, in real memories, we use constant current pulses, not voltage. Yes. Yes, exactly. So that cap is always your supply voltage to the chip is always your cap. You cannot go above the supply voltage that is on the chip. And that supply voltage is typically what is also used in the word line, right? So we use the same supply voltage for the word line. Are there any confusion so far? Any question? No. Okay. Michael, did I answer your question or? Okay. All right. So how much time we do? Oh, we are actually out of time. So I will stop here. We have a few slides left, which I can quickly finish up in the next class. And in the next class, I'll give you an overview of the flash memory so that you can capture the Wednesday lecture well. And don't forget, there will be a 5-minute quiz on Monday's class. And I posted that announcement as well, right? All right. Thank you all. Have a great weekend. We'll start from the next slide. Try to review this if possible before coming to the next class. Thank you.